Hello friends, welcome to part 3 of the first lecture on soil classification. In the first two lectures I talked about the types of soils, the weathering processes, and the second lecture I talked about the soil classification systems such as the USGS system. So in this part 3 of the first lecture, we are going to delve into problem solving. So here's the first problem. Essentially in this problem, you're going to see that there's silt, clay, sand, and gravel. And this graph that goes all the way from silt to clay has been imported from the hydrometer analysis, and they have combined the graphs from the hydrometer and the sieve analysis to produce this whole graph right here. Now in this example here, what we are supposed to do is determine the percentage of gravel, the percentage sand, silt, and clay. And this is what we are really after, because this is what we need to know to classify the soil properly. You could try the example on your own by pausing this video. If not, then the solution is right here. So as I mentioned in the last lecture, what we have to do is look at the graph and look at the sieve sizes, the number 4, number 10, number 40, and number 200. As you would recall from the last two lectures, that these 4 sieve sizes are by far the most important. And among these 4, the number 200 sieve is arguably the most important sieve size, because this is what differentiates between the coarse grain soils and the fine grain soils. So if you were to look at soil A, as I mentioned, that this is a poorly graded soil, and I can tell this right off the bat because this distribution curve is just spanning from number 4 to number 40 and just a point beyond that. So right off the bat, I can say that this is a poorly graded soil without doing any calculation. If you look at soil B, you're going to see that the particle sizes go all the way from number 4 to 0.001 millimeters. And this only signifies that it's a well-graded soil. I don't know what kind of soil it is, whether it is well-graded clay or well-graded silty clay, sand. I really don't know, because I need to look at these numbers here. But just by looking at it, you get a feeling that this is a well-graded soil. So as I said, the focus should be on this number 4, number 10, number 40, and number 200. So if you look at this first graph here for soil A, you're going to see that the percentage right here is 98%. That means only 2% of the soil got retained on number 4, which is why you see that there's a 2% gravel here. Similarly, the sand ranges from number 4 to number 200. But in this case, you can see that it doesn't go past the number 200 sieve. That means the remaining 98% comes in the category of sand, and this is what has been mentioned here. And as I said, it's a poorly graded sand. Now, if you look at the second curve, the soil B curve, you're going to see that the percentage distribution here is close to 100, which means that it's not exactly 100, but slightly lesser than that. And if you were to just eyeball it, it's close to 1% gravel, and that's what is mentioned here. Now, between number 4 and number 200, what do you see on this? So you have close to 40 and 98. That means approximately 61% sand. And if you were to go past this number 200 sieve and look at clays, look at this graph that goes all the way from the number 200 to 0.002, you're going to see that the percentage silt is close to 31%. So just do the math. If you just subtract this 38 from 9, you're going to get 31%. and the remaining 7% is clays. Now, what is the size of this number 200 sieve? It's 0.075 millimeters. And anything that is smaller than 0.002 millimeters is clay. So you have to keep these four numbers as well as these numbers in your mind to discern between silts and clays. Similarly, if you look at the third graph for soil C, you're going to see that this is close to 100%. So the percentage gravel is 0. And the percentage sand, you just have to take the difference between these two numbers here. 100 and it's close to 29, so that's around 31%. That's what is mentioned here. And the percentage silt is 57, and the percentage clay, that means anything smaller than 0.002 is just the difference between these two numbers here, and that is close to 12%. So this soil is a well graded sandy silt. And at the end of the lecture, I'm gonna post a classification chart. I have provided something in the last lecture, but I'll provide a new chart so that you could actually navigate through the various types of soil and the percentage classification. Now, let's look at the uniformity coefficient and the coefficient of gradation problem. As I mentioned in the last lecture, that the uniformity coefficient is D60 over D10, and the coefficient of gradation is D30 square over D60 times D10. Now D60 is corresponding to the 60% size, 60% passing, I beg your pardon. So if you were to look at the 60% passing and come down here, you would get the particle size corresponding to D60. Similarly done for D10 and D30. And this is what has been done here. So if you look at the D60 value corresponding to 60% passing, you're going to see that the size is approximately 1.4 millimeters. Similarly for D30, if you were to look at the particle size corresponding to that, it is 0.95 millimeters. And similarly for D10, it is 0.5 millimeters. Now, as you can see from the question, that we are trying to determine the uniformity coefficient and the coefficient of gradation for soil A. And this is how we got these numbers. Similarly, these numbers can be obtained for soil type B as well as for soil type C. Now, as I mentioned that when the Cu value is greater than 4 for gravels and greater than 6 for sands, and when the coefficient of gradation is between 1 and 3, then it is a well graded soil. If not, then it is a poorly graded soil. Suppose if this is greater than 4, or sorry, if this uniformity coefficient is lesser than 4 and the coefficient of gradation is between 1 and 3, then in that case it would be a poorly graded soil. The reason being that this here is not or, it is and. So both the criteria have to be met, both the uniformity coefficient as well as the coefficient of gradation. Now the question is, for this soil type here, what do you see? The value for the uniformity coefficient is less than 4, which is why it is a poorly graded sand, and that's what is mentioned here. And I mentioned in the last lecture that the symbol for poorly graded sand is SP. So the behavior is the second letter and the first letter is predominantly the soil type, which is why you have sand and poorly graded after. Now this is a very interesting example because we have two soil types here, and what we are trying to essentially accomplish is to manufacture a new soil using the two soil types, soil type A and soil type B, and here is the gradation for that. This would be a very interesting example to solve without even looking at the solution. because essentially what you're trying to obtain here is a uniformity coefficient of 100 for the new soil type C. So to do that, we can use a various combination of soil type A and soil type B. For example, it could be 30% soil type A, 70% of soil type B, which will eventually form soil type C. Similarly, you could use other combinations too. And it really depends upon what kind of uniformity coefficient you're going to get. So what's been essentially done on this problem here is we are going to try different combinations. And the reason we are trying to manufacture a new soil is because we would like to produce a new soil that will compact better. And that is what is mentioned in the question here too. So to do this, what's been done is there was coefficient of gradation as well as the uniformity coefficient obtained for various combinations. As you can see that there's 30% soil type A, 70% soil type B. Then the other combination was 60-40, the third one was 65-35, and the fourth one was 50 and 50. And essentially what was being done here is to determine what really fit the bill or fit the curve, no pun intended, but that's what we are trying to do is fit the curve here. So this soil type, if looking at this 50-50, that is 50% soil type A and 50% soil type B, you're going to see that the gradation curve spans all the way from the left to the extreme right. And that is what we are trying to accomplish. And if you look at the uniformity coefficient of that, it's close to 100. So the best combination is using a 50% of A and 50% of B. That may not be true for all soil types, but for the given soil types, this was the best fit. So if you were to manufacture a new soil based on some existing soil, then in that case you would have to play around with the numbers, use a different combination of different soils to come up with a new soil and see what really fits the curve. Thank you very much for listening. See you in the next